Welcome back. In this lecture, we will introduce one of the two dominant models for nucleus that will be discussed in this class. We will start with the liquid drop model. Before we get on to the model, specifics of the model, let's try to classify in terms of two distinct behavior that helps in modeling a system. A collection of particles can be classified under independent particle models in the sense that each particle either moves independently in the absence of any potential, or it moves more or less independently in the presence of effective potential, and the effective potential is provided by all the rest of the particles. So there is one class of particle. Many a time we can um, model, for example, electrons in an atom using independent particle excitation, in the sense that each electron moves in a mean field provided by the nucleus and the rest of the electrons. Okay, so when you do atomic spectroscopy, that is, you excite an electron, um, a particular electron would go to an excited state. That is, and the rest of the electrons are more or less are not too affected by the presence of this excited electron. That's an approximation. I'm making some loose statements so that we can motivate independent particle, rather than motivate, to contrast independent particle excitation against a different kind of excitation. There are certain collective excitation um, in contrast to independent particle excitation. For example, when you consider a liquid drop, so a liquid drop is always spherical in its ground state because of surface tension. Okay, so surface tension um, as a units of force per meter. It's better to think in terms of surface energy. So the force per meter is the same as energy per meter squared. So the liquid surface has a surface energy which uh, the liquid drop tries to minimize by having the least surface area. For a given volume, the spherical shape has the least surface area. Therefore, therefore, the surface energy is also minimized. So if you consider the excitation of a liquid drop, any excitation from a non-spherical um, shape is an excitation. That is, supposing it takes an ellipsoidal shape. So this excitation is not because of excitation of a single particle, but it is an excitation of the entire drop itself. So these kinds of excitations are collective excitation. Interestingly, there are a lot of evidence to suggest that nucleus also undergoes such collective excitation, and because of such collective excitation um, and few other features of the nucleus, uh, the liquid drop model was proposed. So, because this is not at all intuitive, right? So, liquid is sort of a very classical object, which perhaps is very, very different from nucleus. So, it is not at all intuitive why a nuclear matter should be modeled via a liquid. The way we think about a liquid, we will see why uh, it has credibility, because there is a lot of power in the prediction of this model. So let's also understand and contrast forces that are operational in the fluid, if the fluid is a gas, or if the fluid is a liquid. In the gas, what differentiates it from a liquid is that there is certain mean-free path between collisions. Typically, a gas molecule atom is not in contact with other gas molecule atom, so it can traverse to a certain extent and then collide and then change direction. Okay, so this kind of um, motion is possible because there is weak interaction between a gas molecule atom. So the forces of interaction between atoms and at gas molecules is very less. Okay, so this facilitates movement of gases. In contrast to this, the liquids do not have this concept of mean free path because the liquid is always in contact with other liquid molecules. Therefore, it cannot really traverse to a particular distance without touching any other um, liquid molecules. So, this concept of mean free path is distinct to gases and indicative of weak interaction between gas molecules. So when you have a liquid, there is both repulsive and attractive interactions. If there are no repulsive interaction, the density will keep increasing. And if there is no attractive interaction, things will not liquefy, right? So when you say you have an ideal gas, the ideal gas never gets condensed into a liquid because there are no interactions. So if you say that something forms a liquid, that means there is strong attractive interaction which makes it condense into a liquid state. But even in the presence of this attractive interaction, there's also a repulsive interaction. A balance between these two determine the density of a liquid. Likewise, if you consider an nuclear matter to be liquid, there has to be attractive and repulsive interaction. You can anticipate what can be the nature of this interaction. For example, the strong nuclear forces provide an attractive interaction to keep the to facilitate the formation of nuclear matter. And there are also Coulombic repulsive terms because of protons confined inside the nucleus that may provide the repulsive terms. So if you so in a liquid, even in depending on the liquid, there are variety of forces, but all these forces are relatively uh, simpler compared to what is present in nucleus. So there can be much of these forces in a classical liquid is modeled via, let's say, Lennard-Jones potential. This is attractive at large distances, but strongly repulsive at short distances. So that is a model for interaction between molecules in a liquid. So if you look at nuclear liquid or nuclear matter, the forces are much more complex, and we will not spend a lot of time into this because uh, we have to go into the realm of particle physics to give a detailed exposition of the nature of forces uh, that are operational inside a nucleus. But we will just say there are something called pi meson fields, which make these interactions possible. So the strong nuclear forces do not differentiate between charges. That is, the strong nuclear forces are operational between proton, neutron, neutron, as well as proton and proton. So the way, very qualitatively, there are certain particles that are exchanged between these nucleons that are interacting. For example, proton may decompose into a particle called pi meson, pi plus meson, and then that may further react with the neutron to form something else. So this n prime is something that comes from p, this proton. Likewise, this neutron can decompose into P prime, a proton, and pi minus meson. And so this may combine with a proton to form a neutron. So that is qualitatively what we are trying to say is there are some particles called pi mesons which are exchanged between the nucleons, giving rise to attractive strong nuclear forces. So with that, we need not get into the details of these forces to model the nuclear structure within the scope of this course. So the assumptions of a liquid drop model is that nucleus is like an incompressible and homogeneous liquid. Okay. So what do we mean by that? That is the density of the nuclear matter does not change, and it is uniform within the bulk of the nucleus. Then the strong interactions are operational within the nucleus. They provide the attractive interaction. These forces, as mentioned in the previous slide, are charge and spin independent. Okay, so it doesn't really differentiate between proton neutron, neutron neutron, proton proton interactions, and it's also independent of the spin of the particle. These are all assumptions, and nuclear forces are very short range. We'll see the consequence. It's more short range than Coulomb interactions. Uh, so it is operational such that each nucleon is interacting only with the nearest neighbor. Okay, so it doesn't even feel uh, the interaction of the second nearest neighbor. So these are the assumptions. The proofs or the validity of these assumptions depends upon the predictions made by the liquid drop model. We'll see it's a fairly powerful model which has great explanatory power. So that is why still some aspects of liquid drop model is used. So how do we go about quantifying a liquid drop model? So as I mentioned in the previous lecture, this is not a first principle model. Okay, so this is a phenomenological model in the sense that we will fit the constants that is required for liquid drop model to some nuclear structure. Supposing we have 5 constants in this model, these 5 unknowns can be fitted using the data of 5 nuclei. But the validity of the model relies on using these fitted constant. You can predict a variety of other nuclear structure, right? There are hundreds of nuclei structure. Using a limited fitted data, you can go about predicting the properties of many other nuclei. That's why the liquid drop model is very powerful. So the way we want to be looking at this is you decompose the binding energy. What do we mean by that? If you consider the nuclear matter to be like a liquid, there is a binding energy associated with the volume, that is the inner part of the nuclear liquid, because the surface has lesser coordination compared to the bulk, that is compared to the volume inside the nucleus. The binding energy of the surface is different from the binding energy of the inner volume. Then there is this Coulomb interaction because of protons that exist inside the nuclear matter. Then there is something called asymmetric energy. You will see why this is so, because there is an asymmetry in terms of neutrons and protons that will be accommodated into this term. And then there will be something called pairing energy, okay, because neutrons and protons are fermions. There is something called a pairing energy that will also be incorporated. So the total energy of nuclear matter, which is to be modeled as a liquid, will be decomposed into these five terms, which will also give rise to five constants, which can be fitted to five nuclear. And then using that data, we will, using these constants, there will not be any more fitting, and we'll try to predict the properties of variety of other nuclei and even few phenomenon like beta decay and alpha decay and so on. Okay, so this is a very powerful model. um, it's exercise in modeling fairly complicated nuclear structure. So it's a very beautiful model, even though it's fairly simple. What makes it very beautiful is uh, that fairly simple expressions can give rise to predicting fairly complicated phenomena. So we in the next lecture we will elaborate the details of the liquid drop model. Um, this is eventually when we end up with the uh, total energy, because the energy corresponds to mass. We will come up with a formula. It is semi-empirical because some experimental data will be utilized for fitting the constants of the model. This is first uh, got into a complete shape by von Weizsäcker. So uh, this is the model we'll be discussing in the next lecture. Uh, thank you.